So I'll record my own video, which I'll put up using this screen or whatever it's called, screencast software. So you only get one window rather than all the different windows you get with the video, but I'll also record the video as well. So if you look at it here, this will be question 2A on the paper. Sorry, question, not 2A, question 1B, and also question 2B on the paper. Okay, so there'll be two versions of this on the paper. So integrals are products of type. Basically, it's the method of substitution for products and quotients. Now, I know you did a bit of this last year, but this kind of presents a different way of doing it, and it's given here in the overview. The equation y is equal to 2x plus 1 times x squared plus x plus 1 is a product of two terms. So this is the first term, term 1, and this is term 2. The smaller linear function on the left, so you have this one, linear function. So remember, what do you mean linear function? If you plot it, it goes through 1 when x is equal to 0 and has a slope of 2. So y is equal to 2x plus 1. So you plug in x equal to 0, so you know it goes through 1 and has a slope of 2. So I've drawn it with a steep slope there. And a quadratic function on the right. So this is your quadratic function here. In this example, the linear function is the first derivative of the quadratic term. For any product of two terms, so if you look at here, the quadratic term is x squared plus x plus 1. So if I differentiate that, I get 2x plus 1. So what you're saying here is term 1 is the first derivative of term 2. For any product of two terms, the method of substitution can be applied to determine the integral whenever the condition holds that one term is equal to or is a multiple of the first derivative of the other term. In this chapter, the method of substitution will be demonstrated for a range of examples of increasing complexity. So some examples are given. So in this case, so this is an overview of the sort of questions that will be asked. In this case, first derivative of the larger term is a multiple of the smaller term. So if I get the first derivative of this, it's 2x plus 1. If I double that, I get 4x plus 2, and that is equal to the second term in the product. So basically, in this case, a times the first derivative is equal to, that should be g at x being this function here, or 2 times 2x plus 1 is 4x plus 2. Okay, so there's a typo there, that should be g at x. And the way you say it is, you say f at x and g at x and f prime x for the first derivative. So in this second example, is everyone okay with that example that I just showed? I'll just do a quick poll. Everyone so understands the example I just said, yeah? That we're just looking here, it's a product of two terms. And all we're saying here is that the bigger term here, if you get the first derivative of it and multiply by 2, you get the other term in the product, which is this one. Okay. So if we keep going with that, in this case we have a product of two terms, this one and this one. The term in the Killian, your microphone's on there. The second term is raised to a power that's a positive integer, and the first derivative of the larger term inside the brackets is equal to the smaller term. So once again, this time we have a quadratic here, but it's brought to the power of 3, and then you have the second term. But it's still valid to use the method of substitution in this case. If I differentiate the larger term, I get 2x plus 1, and that is equal to the second term in the product. If we then look at this example, the second term is raised to a power. In this case, it's a positive fraction. And the first derivative of the larger term inside the brackets is a multiple of the smaller term. So if I look at this one, the first derivative is 2x plus 1. If I multiply that by 3, I get 6x plus 3, and that is equal to the other term here. So what it's basically saying is setting it up that all of these, you can use the method of substitution in all these cases as long as this condition holds. Okay, so we come down here. It is found that the general formula shown here can be applied to all cases. This method can be quicker than the method of substitution, which you've done last year. Before the formula can be applied, a test should be applied to establish that one of the terms is equal to or is a multiple of the first derivative of the other term. So you've done this last year, but what we're doing here in this section is presenting a quicker way to apply this method of substitution. And it's basically saying here that if we have a product of two terms and the condition holds that one term is a multiple of the first derivative of the bigger term, then we can apply this rule here. Now it's valid for all values except n equal to minus 1, n equal to minus 1. So if we look at we can actually see here how it can be used if we have a fraction or a quotient. Here we have 4x plus 2 divided by x squared plus x plus 1 to be squared. And all you do is you have the plus 2 here. You can bring it up here by changing this to a minus 2. And once you have it in this format, you're able to apply this formula again. So the denominator can be brought to the top by changing the sign of the power, and the first derivative of the quadratic is multiplied by 2 to give the denominator. So let's look at this example here. If I then differentiate this, I get 2x plus 1. And if I multiply by 2, I get 4x plus 2. And that is the denominator, or the other term here in the product. Okay, and then once again it can be applied to this case here, where once again I have x squared plus x plus 1. Now I noticed last night when I was going through this I have a mistake here. That should be minus a half, not plus a half, because you're bringing it up on top, so the plus a half becomes minus a half. If I look at this one and differentiate the bigger term, 2x plus 1, I multiply by 3, and I'll get, if I multiply by 3, I get 6x plus 3, which is this term up here. So once that condition holds, I can use the rule that I see up here. And then this last one is what happens when n is equal to minus 1. This rule works for all cases except where n up here is equal to minus 1. So this symbol here means for all. So this is valid for all cases except where n is equal to minus 1. For all n not equal to minus 1. So what happens when n is equal to minus 1? Well, in that case you use this rule. And this rule is basically you have a quotient here, you bring that up on top, so n is now minus 1. And the derivative of this is a log f at x, like so. A times the log of f at x. So if we look at this formula here, if I run through this one here, the integral of 4x plus 2, I bring this one up on top, x squared plus x plus 1 to the minus 1 dx. So now I'm going to use this rule because I have a minus 1 up there. That's equal to a. Now, first of all, what is a? Well, if I look here, the derivative here is 2x plus 1. And I have to multiply that by 2 to get 4x plus 2. So my multiplier there, a, is equal to 2. So you get the derivative, and what you have to multiply that derivative to get the other function. That's the methodology you're using. So in this case, a is equal to 2 times the log of x squared plus x plus 1. And that's it, plus your constant of integration. Now I have an f in here. I have to tidy up these notes. There's no need for that f there. So I've given an overview of it. We're going to go through these in detail anyway. Is everyone happy enough with that? That this is the range of problems. You have two rules basically. This is rule 2. And you apply this when n is equal to -1. And this is rule 1, which you apply in all other cases. And that's when n is not equal to -1. Okay. Now, I'm going to just do one of these. This is your method of substitution. What I have here is a load of examples where we do it by the method of substitution that you would have seen last year. I think you saw this last year with Edmund. So if I look at this here, did you see this format before, method of substitution? No? One person saying yes, but a lot of you say no. I thought it was on the course last year. Okay, the idea here is you have one of these products here. So what we do, and in this case, you'll find that this term here is a multiple of the first derivative of this term. This is the way you do it with the method of substitution. So I'll do a few of these, but then I'm going to just stick to our method. So we say, let z equal to the bigger function. So let z equal to the larger term in the product. Let the larger term in the product equal to the variable z. Differentiate the function. dz dx is 10x minus 1. And then what you do is you basically substitute that in. So if you look here, we have 10x minus 10. We put dz dx in for that, so we substitute that in there. We have our dx's here, and we have our z. So I'm going to do it up here. If I write it this way, write it the other way around, 5x squared minus 10x plus 3 times 10x minus 10 dx. That's what we're differentiating. So what we do with the method of substitution, if we let z equal to this, I replace this term here with z. I differentiate z, I get 10x minus 10. So for the 10x minus 10, I put in dz dx. And then I just bring this dx down here. Now what happens here is we have a dx above, a dx below, so that cancels. So what we have is the simple integral, the integral of z dz, and that gives me z squared over 2 plus my constant of integration. And then all I do is substitute back in what we started with here. So 5x squared minus 10x plus 3, all divided by 2 plus the constant of integration. Now I've run through it here, but you can see it's all done in here. But that's the standard method of substitution. Did you not see that last year? Did you see that last year? So most of you are answering no, but that's the traditional way you'll find for the method of substitution. Everyone's saying no there, so that's fine. And the general rule here then is a visual inspection shows that the following formula will apply to these cases. So if you have a function and its first derivative as a product, the integral will be the function to be squared divided by 2. So in practice, you must spot that one function is the derivative of the other or some multiple of it. If we come here to this more advanced case where we have a product in front of it, we say let z equal to the bigger function, get the first derivative of it, and then we'll see that we have to derive to get this term here. Our first derivative is 10x minus 10, and to get this here, we have to divide that by 10. So 1/10 dz dx is 1/10 of 10x minus 10, which is equal to x minus 1, and that gives us the one over here. So we know our multiplier there is 1/10. So what we do here is we substitute in for dz. For this one here, we substitute in 1/10 dz dx. Okay, I don't like that one there. It's too, you can't see it. I'll do it in yellow maybe. So you substitute that in for that. For the z, you substitute in this for the z, and the delta x is just copied over. So because you haven't done this, I'm kind of going to skip ahead and just say this is your standard method of substitution. But you'll find that you end up, what I'm moving towards here is how do I derive that general formula? But most of you haven't actually seen this. So because you haven't seen it, I'm going to skip ahead and just present our method so as to avoid confusion. And I'm going to skip ahead here to our first worked example for our method here. What I'm basically saying is all these pages here are the traditional method here. And what I'm trying to show is that we end up with this equation here, a general formula here, which is the one I already presented to you earlier. And these are the formula that we're going to use. And this is the methodology that we're going to use. So we'll go straight to this, and I have the videos done for the first 7, which you can start working through in a while. But if we look at this here, and I go through here, this is the methodology. So we have a function here. Something happened there? Yeah. You don't know. For my exam, you don't have to know the traditional method. That's not to say you won't see it in books and you won't see it elsewhere. But for the purpose of my exam, we're going to do this method here. Okay, is everyone happy enough with that? I was presuming that you'd done this last year because it's on last year's course. But maybe with COVID or whatever, it wasn't covered, you know. I think that's probably it. It just wasn't covered because the course last year was curtailed. So if we look at this, we have a product here. So this is your methodology. Step number 1, let f at x equal to the function with the higher power. So f at x is equal to a x squared plus 4x minus 1. Let g at x equal to the other function, 4x plus 8. Then evaluate the first derivative of f at x, so we get 2x plus 4. 2x plus 4. Then what we say is calculate the multiplier. And what you do to calculate the multiplier, this is the one you have to remember, is I'll do it here, you get the coefficient of x in g at x, and you divide it by the coefficient of x in f prime at x in the first derivative. So you divide the 4 there by the 2, and that gives you a multiplier of 2. And then before you use the function, you test, is it valid to use this? So you say, is a times f at x equal to f prime of x equal to g at x? So that's saying, is the first derivative of the bigger function a multiple of the second term in the product? So you have a product here, you have term 1 and you have term 2. And you're asking, is the first derivative of term 2 a multiple equal to or a multiple of term 1? If that is the case, so we have a multiplier, we've worked it out here, so we say, is 2 times the first derivative equal to the other term? Yes, it is. So once you've established that, that says, yes, I can use my rule. So if I come here, you can see I've written it out in full here. A, in this case, is 2. So this is what you start with. And that is equal to, so if I underline this one, that's g at x. And that can be replaced with a times f prime of x. Okay, the function is the function f at x. That's f at x. So you're saying once this condition holds, that we're dealing with a times the first derivative of f at x times f at x, then we can say that that is equal to a times f at x n plus 1. So remember, n here is, if there's no power here, it's automatically to the power of 1. So we add 1 to that, we increase it by 1 to 2, and then we divide by that raised power 2. And that's what this rule up here is actually saying. That in this case, n is equal to 1. So n will become 2 up here, and we divide by 2. And that gives us x, the 2's cancel above and below. So that gives us x squared plus 4x minus 1 to be squared. Okay, so that's that one there. Let's look at this one here. This is where we have it to the power of 4. Now it doesn't matter that the power is here. All we're saying is that f at x is this one, and g at x is that one. So following the methodology, if I do it up here, I have this in the notes anyway, but I'm just going to do it here. So step number 1, okay, hang on. What I'm going to do is zoom this up. And I'm going through bit by bit. So I'll do the calcs in here basically. So we say let f at x equal to the bigger function. So f at x is equal to, you can see it up there, x squared plus 4x minus 1. G at x is the other function. Now remember, you don't include the power when you do f at x, you just take the function inside the brackets. There's a power of 4 there, but you ignore that for the moment. And then you ask, evaluate f prime at x. So this one up here gets the first derivative. So f prime of x is equal to 2x plus 4. Then you calculate the multiplier, a, by taking the coefficient of g at x here, the x in g at x, and you divide it by the coefficient of x in the first derivative, and that gives me 2. Then the question is 2 times the first derivative, so this is my f prime x up here, equal to g at x? And that is asking, is 2 times 2x plus 4 equal to 4x plus 8? The answer is yes. Is everyone okay with this so far, the methodology so far? If I just answer yes or no, you can see I'm just following a set procedure here. And this is the simplest way to do these. If you follow systematically this procedure each time, if and only if the answer is yes, apply the general formula to the integral. In this example, n is equal to 4. So that's our general formula here. So I'll apply it here maybe. So what we're saying here, now I've already written this stuff out, but I'm just trying to do it here. So a we said was 2. F prime x is 2x plus 4. So you're replacing g at x with these terms. And then we have the main function is, what is it? X squared plus 4x minus 1. And that's to the power of 4 dx. So if we apply our, if we apply our rule here, and I'll just scroll to the left, I'm applying this rule here. You can see I have it written down below, but I just take a, so a is 2. Our function here is x squared plus 4x minus 1. The power was 4, so we add 1 to that to get 5, and we divide by the 5. And that gives us the integral of that function. So if you look at the system that you follow, you look at the procedure you follow, you have a rule, but you run through this procedure and you validate that by here, in this step here, you validate that it is possible to use the rule, that it is okay to use the rule. Okay, now I am going to, there's more examples here. And I think this one here, I'm going to pause this video here. So in this example, we have this one, a product, but this time we have a square root. So of course what we do is we rewrite the square root with the exponent of a half. So we have 4x plus 8. This is function number 1, and we're going to let that equal to g at x. And function number 2 here, we're going to let equal to f at x. And the only difference here is instead of having a whole power, we have a fraction. So if we run through this, again, I'm going to maximize it the way I did before. So this is as if I'm running through it myself. So we let f at x equal to x squared plus 4x minus 8. G at x is equal to 4x plus 8. And first thing we do is we get the first derivative of f at x. So it's x squared is 2x plus 4. Differentiating that one. And then to work out a, we divide the coefficient of the x here by the coefficient of the x in g at x by the coefficient of the x in the first derivative. So that gives me 4 divided by 2, which gives me 2. And then the question is, I've worked that out, so the question is a, which is 2, times f prime x, that is equal to 4x plus 8, and is that equal to g at x? That is equal to g at x. That means we answer yes. So we validated that that's correct. Did I do something wrong there? I did something, hang on there. This should say n is equal to 2, not equal to a half. So if we come along here then, and this means we're going to apply our formula over here. So all I have is my formula here. So I'm going to write it out here. Over here, start over here, so I have room. So a is equal to 2. F prime x is 2x plus 4. So that is a times the first derivative of f times fx, which is, I have to go up to find it, x squared plus 4x plus minus 1, x squared plus 4x minus 8. So sorry, I just have a typo here. That should be minus 8. Obviously, I'm cutting and pasting these. So it doesn't really matter what that constant is, actually. What do I have it as 1 down here, so I leave it as 1. So I'll just leave it as 1 up here. There's a bit of a typo there. And I'll leave it as 1 here. So if I follow it here, that it's actually 1, it's x squared plus 4x minus 1. And that's to the power of a half dx. And that is equal to a, which is 2, times x squared plus 4x minus 1. And we have a half here, so we add 1 to a half, we get 3 over 2. And we divide by the 3 over 2, plus a constant of integration. And as we said before, if we divide by 3 over 2, that is the same as multiplying. You can see it's done down here. It's the same as multiplying by 2 over 3. So if you look at it here, we have, if I do it here, that gives me 2 times 2 over 3 times x squared plus 4x minus 1 to the power of 3 over 2. And then you can see it here that we have 4 times x squared plus 4x minus 1 to the power of 3 over 2 divided by 3. That gives me 4 thirds x squared plus 4x minus 1. I split the 3 over 2 into 3 times a half. So the 3 then tells me that I'm bringing everything in the quadratic equation there to the power of 3. And the half tells me I'm getting the square root. Okay, so somebody asked a question there. Why is it minus 1 in the f at x? So if you look at this, that's the integral of tan of 2x squared times sec squared 2x dx. Now the thing about it is, if you look in your log tables, the derivative of tan of x is, if you look at your log tables, derivative of tan of x is sec squared x. Okay, that's in your tables. So if we look at this one here, we start off, now you have to know that, if you know what I mean. It's not, you have to kind of be able to recognize that. So if you see a product of two trigonometric functions in one of these questions, you can be sure that one of them is the first derivative of the other, or multiple of it. So if we look at this, f at x is equal to tan 2x. G at x is the other function. I get the first derivative of f at x, and if I do that, it's like the chain rule here. And the outer function is the tan of x, and the inner function is the 2x by the chain rule. So if you look at it there, the integral of tan of 2x is sec squared 2x. So that's the outer function. And then the inner function, the derivative of 2x is equal to 2. So that's the, by chain rule, that's the inner function. Okay. So then we say calculate the multiplier by dividing the coefficient of sec squared 2x in g at x by the coefficient of sec squared 2x in f prime of x. So in g of x, the coefficient is equal to 1. So that's my 1 here. And in the first derivative, the coefficient is 2. So my multiplier is a half. So it can be quite tricky doing these trigonometric functions. So the question then is this test valid? So a is a half times the first derivative equal to the other function, sec squared 2x, and the answer is yes, it is. Yeah, it is equal to g at x. Therefore, we're able to use our function here, and in this example, n is equal to 2. So this is my a, this is my first derivative, this is my function f at x, and the power here is 2. N is equal to 2. So what we get here is a, then n was equal to 2, so n is increased to 3, and then we divide by the raised power, so we divide by the 3. And what this gives us then is the tan of 2x to be cubed divided by 2 times 3, giving us 6. So there'll be one of those in the handout as well, yeah. Okay, is that one's tough now? That's handy, and that's a hard one. That takes a little bit of getting used to.